the internet today. Today's speaker is Dr. Igor Paprotny. He is one of us. He's from UC Berkeley, a postdoc. His advisor is Professor Richard White. Igor is with the Berkeley Sensor and Actuator Center. His research interest includes MEMS sensors and actuators, smart grid MEMS sensors, micro and nano robotic systems, and application of MEMS to physical computing paradigms such as quantum computations. He is presently involved in applying MEMS technologies to develop distributed microsensors for environmental monitoring and electric power distribution systems. Dr. Paprotny received his PhD in computer science from Dartmouth College. He also holds an engineering diploma in mechatronics from the NKI College of Engineering in Oslo, Norway, as well as BS and MS degrees in industrial engineering from Arizona State University in Tempe, Arizona. So let's welcome Dr. Paprotny.
Yes, thank you very much for that introduction. And thank you all for coming to hear my talk here today. And what I'm going to be talking to you about is the work in our lab on essentially creating these low-cost, wirelessly enabled sensors that can measure electrical quantities as well as diagnostic quantities for electrical circuits. And we believe that this technology, so what we're actually going to do is I'm going to show you how we use MEMS technologies to reduce the cost of the sensors, and in such a way that we can actually enable a massive deployment of these sensors, hopefully for the future smart grid. So this is a brief outline of the talk. I'm going to sort of motivate the problem to tell you why I think MEMS is so well applied to the problem of smart grid sensing. I'm going to introduce the MEMS, wireless MEMS sensor module. Talk about specifically two components of that module, which is the MEMS proximity sensing, which we use to sense these operational quantities, and also energy scavenging that allows this module to receive power throughout its lifetime. And then, of course, conclusion at the end. But before we move on, I would like to acknowledge both a few people as well as our funding sources. I sort of like to do this in the beginning of the talk where I have all of you's attention. This is actually very important. So I would like to acknowledge my advisors, Richard White and Paul Wright, who are running the lab and also providing the guidance, direction where we're going. I'm also very fortunate to work with some very talented students and postdocs, and some of them are actually in this audience here. Specifically, Richard and Y1, their work is on the energy harvesting, sort of the big Mesoscale energy harvester that I'll be talking about later today. Giovanni and Mike Seidel. Mike is right there, actually, in the audience. Mike? Hey. Okay. Oh, and there is Richard Su and Y1. Hey. Say. Okay. Anyway, so Mike and Giovanni are working on some of the diagnostic sensors I'll be talking to you about. And then we have Chris Sherman and Eli Leland. Eli is actually gone to Washington, D.C., but Christopher is now running the show here on the MEMS current sensor. So some of the sensor technologies we'll be talking about. And I also would like to acknowledge the funding, specifically the ongoing funding from the California Energy Commission that drives this research forwards and really allows us to explore some of these exciting things I'll be talking to you about. Now, as well, of course, as some funding and infrastructural funding from both the Berkeley Sensor and Actuator Center, as well as CITRIS, Center for Information Technology Research in the Interest of Society. All right, so the U.S. power grid. According to the Department of Energy, this is the largest interconnected machine on Earth. And the size of the system is really amazing. You can see here a map. This shows just the transmission lines, and of course, spans the entire continent. things like, over 900,000 generating units, 1 million megawatts of capacity, 300,000 miles of transmission lines. So, the size of the system is really immense. And the interesting thing is, it contains components that are newly installed, as well as components that have been there for decades. And so the problem is that this huge machine is actually aging. Both the Department of Energy as well as the data I have actually here is from an article in CNN about 2 months ago. We can see that there is an increasing number of blackouts in the United States. In fact, over a period of 2 decades, that number increased by 126%. And so the reason for that is that we have this sort of aging infrastructure in the power grid system. The cables are aging. Some of them have been in the ground for over 50, 60 years. Of course, not all blackouts are as dramatic as the one that is shown here in this picture. This is from a satellite taken on the 14th of August, 2003, right, during the Northeast blackout. And you can really see this amazing impact that blackout caused on the Northeast. The cost of that blackout estimated just for that one event was over $6 billion. So, staggering cost, right? And in fact, at that particular time, I was right here trying to buy medicine for my son, who developed a very high fever. And I couldn't find a store that was open, because everything was closed because of the blackout. So finally, I was on Long Island. There was one place that had a generator, after driving around, and the fever get higher and higher, and I was able to buy some Tylenol. So personally, for me, I sort of felt how important it is that the power infrastructure is really, we really avoid this type of disruptions, right? Okay, so that's, we have this aging infrastructure. Now, on the other side, if you look at the statistics for putting money into the infrastructure, that money is actually less and less. So just looking at data for investment in transmission lines, the amount of money that coming in to replace and build new infrastructure was reduced by half from 1975 to the year 2000. And that reduction is slowly continuing, right? So we sort of see an asymptotic value now is approaching close to $2 billion. So aging infrastructure, yet there's less money being put into to fix that infrastructure. If that wasn't enough, there is the renewable energy penetration problem. So we are, in California, for example, we're at the forefront of that. There is a mandate to put a 33% of renewables into our energy generation portfolio by 2020. And so that's great. It definitely allows us to sort of be on the forefront on capping the carbon emissions. However, the problem is that renewables introduce variability into the system. The wind blows or it doesn't, the sun shines or it doesn't. The cloud comes over the power plant, and all of a sudden now that supply drops down dramatically, another plant has to be brought up to essentially provide power to support that demand. And people can say, well, so why don't we just put these solar power plants where the sun always shines? In fact, this graph here shows daily output of a power plant in Springville, Arizona. So even though it's in places where we know there is abundant sunshine, we still have to account for this variability. So aging infrastructure, reduced funding for building up the infrastructure, and increasing variability. That sounds kind of like a bad news. However, there is this push to completely upgrade the power infrastructure in this country, and that's called the smart grid. And so the idea with the smart grid is that it essentially provides a self-healing system that adapts to changing conditions of this grid. So, for example, in this diagram, you can see we have some industrial plants right here that provide power into the system. There is some distributed renewable resources. For example, we have wind, solar, rooftop solar right here. There are office buildings. We have some residential housing places. And so the idea here is that now we have sensors and an information infrastructure that's overlaid over the smart grid. And the grid actually adapts dynamically to things that are changing, or at least that's the vision. So for example, if we have a lightning strike and an outage on one section of the grid, the grid can now automatically cut off that section and prevent this fault to spread to the rest of the system. Things like routing the power in the optimal way. So essentially using the existing infrastructure, transmission line infrastructure, to move the power between a variable supply and a variable demand. Right? The push for demand response, which again allows the individual loads at both in the offices, let's say, or the residential setting to be shaved off to actually reduce demand during peak times. Right? That's all part of this smart grid. And so looking at it from a MEMS sensor perspective guy, I'm thinking that means a whole lot of sensors. There's just a massive need to put these sensors, pretty much everywhere. Sensors that monitor how this power flows through the grid. Sensors that monitor the faults in the grid. Sensors that look for how much power we're using and how to best shed those loads. And we're talking about the whole entire grid here. From a MEMS guy, that's really exciting because we're really good at making things, a lot of them, really inexpensively. And so that's where I think really MEMS can help the smart grid. So again, I believe that's an opportunity for MEMS. MEMS, as many of you know, but some might know, stands for micro electromechanical systems. And what it means is that we can actually take mechanical systems and make them really, really small. In fact, we make them so small that the size scale of the mechanical components approaches the size scale of individual transistors in integrated circuits. So, going back to the need for many sensors, the numbers are really staggering. So, for example, PG&E estimates that on their network alone, they need 900,000 sensors. So that's actually looking at their distribution network. And that's about, distribution and transmission network. It's about 1 sensor per 15 people. And this is, again, sort of because, thinking about just monitoring the power flow in the network. However, if we made these sensors really inexpensive, then we could dramatically increase that number. So I think this is a very conservative view, right? We would envision, having 10, maybe 20 sensors per person, right? All in our homes, monitoring how we use the power, if we can make these things really cheap. But still, even though, with those numbers, we have quite huge numbers of sensors that are needed just for monitoring the power flow over the grid in both the US and California. Looking at some of the current technologies out there, for example, state-of-the-art sensors that are often measuring these voltage, current, power factor, quantities, harmonics at the distribution station level. They cost about $3,000 per node, right? So, if you would want to instrument the grid, you can't with those numbers, right? That's just too expensive. If you're looking at some of the lower-end cost sensors, they are, of course, a lot less cheaper, but still, a clamp on amp meter, it's about $100 or $200 per amp meter. We've seen some solutions that are wirelessly enabled that approach, $75 per solution. And then the really low-end applications that we can buy for our home, that's about $20. Okay, so with MEMS, we project that we can reduce the cost of these sensors by 1 to 2 orders of magnitude. And the reason we can do that is that we can take, we can use exactly the tool set in MEMS that we've used before to reduce the cost of accelerometers, to make these accelerometers be really prevalent in airbags, to look at filters in cell phones, right? We all have MEMS in our cell phones now, MEMS components. And that is batch processing. We can process many of these units at the same time. We can do wafer-level integration, so we can actually do, again, batch wafer-level integration, or we integrate components on wafers themselves. Allows us to do many things in parallel. And we can use novel materials, which allows us to use cheap materials when we need to, and only use silicon and more expensive materials when the need really calls for it. So that's on the cost side. If we make these sensors really small, we can reduce the installation cost, which is the other big factor in sort of instrumenting the grid. We can make these sensors to be really, really small, and that's actually where sort of our technology, which I'll be talking about today, is going. They can be really small, the size of a memory stick, makes it easy for these things to be installed. They can be sort of stick-on installment, or if they're really small, they can actually be embedded into new equipment. And so there is now a big push around from the different equipment manufacturers, such as washers, dryers, things like that, which are coming out with already built-in sensors that will then monitor the power use of those equipments. Those are smart appliances. If we make these sensors that we're saying are really small, what if they can be embedded in every power cord? What if we can we buy a power cord in the store? What if that power cord already has a sensor in it, just like all cell phones have a GPS in it right now? And then if we choose to use it, we can actually monitor the power flowing through that cord. So, again, using MEMS can help us to actually do that by making these sensors really small and then self-powered. There is a great deal of research actually at Berkeley already in low-power radios. We're actually going to use some of these radios into our modules. So MEMS can really help us to sort of reduce the power requirements needed for these sensors and for radios. And so that's great, because then using MEMS again, we can develop energy harvesters that help us to actually extract a little bit of power from the circuits that we're measuring, and to power these sensors essentially indefinitely, right? Provide power to power the sensors. And so that becomes really important, specifically when we look at diagnostic sensors. So for example, if we're putting a sensor into an underground power distribution cable, and that sensor is supposed to tell us when that cable is going to fail, that cable is going to fail after 20 or 40 years, right? So we need that sensor after 20 or 40 years of installment, the cable is underground, right? To tell us, okay, now, to start sending data, now it's time for this cable to be replaced. So we need to have the self-powered ability. And so, together, I think really sort of MEMS is the enabling technology for a lot of these exciting applications that we can imagine for the smart grid. So this is essentially the topic of the talk today. That was sort of a long introduction, but I think it was important to motivate the problem. This is what we're working on right now. We're working on this self-powered, wirelessly enabled sensor module that uses MEMS technologies that is really small. It's the size of a memory stick, and it allows us to collect these quantities that I just talked about, using power obtained from the actual circuit that it's measuring. So it consists essentially of three main components: MEMS proximity sensors, which sense voltage, current, power, also some diagnostic information, MEMS energy harvesting, which then provides power to both the sensors, and the radio mode that's also embedded in this system that then sends out the information to a low-power mesh wireless network. Of course, there are other components as well that are important. There is also the packaging. So it's important that this system will be hermetically packaged to improve its longevity. It also allows us then to do this packaging at the wafer level, right? So we can do wafer level packaging, package them in batches. And so we're actually working with a company that is very good and researching ways to do that packaging very efficiently. And then, of course, there's also other work in this center as well as in CITRIS on printed energy storage. And we envision that would be also an integral part into this unit, because, of course, you need to store the power that you're harvesting from this energy scavenger in order to then use it in burst when you need to actually transmit information through the radio. So for the radio mode, we're actually going to use some of the existing hardware, so we're actually not going to address that at all. These are also solutions that I'm not going to be talking about. In fact, I'll focus the talk on these these two things here, so the sensing and the energy harvesting. So for the sensing, we're looking at current, voltage, and power. We have some MEMS solutions there. In fact, because Chris Sherman, Eli Lilly developed this, so this is a working MEMS AC current sensor. And then we're looking at some diagnostic things. And in fact, for the diagnostic sensing, we're sort of leveraging some of our earlier work on looking at underground power distribution cables. And for the harvesting or energy scavenging, to extract the power from the circuits, we're actually looking at two different designs. One is a mesoscale design, which is a larger size energy scavenger, but then at the same time developing something that will more readily fit into this form factor, which is a MEMS scale energy harvester that essentially is the size of an integrated circuit that can then harvest the power and provide power to drive both of these two other components. So I'll talk about that as well during this talk. Now, of course, this is really sort of the version 2.0 of our wireless sensing node. So Eli Leland and Chris Sherman actually developed version 0.1 when they did their proof of concept testing of their current sensor. So they actually put together a whole self-powered module. It's a little bit difficult to see, but it contains a sensor, a MEMS sensor die. This is just for the current sensor. Some amplifiers to drive to actually enhance the signal from the current sensor. They had an energy scavenger here, which is just a big beam with magnets on it, and then some power conditioning circuit and storage. And they were actually able to run this thing and just to show that you can, in fact, harvest energy and then use that energy for measuring currents in a nearby conductor. So sort of going back to talking about the long-term goal, as I said, it would be really exciting if these things could be so inexpensive that we could really sort of permeate our homes and both transmission and distribution systems with these low-cost sensors. And so, for example, one of our sort of goals, this will be, I believe, version 4.0, if you would, of that self-powered wireless sensor would be, what if you could go to, say, Home Depot and buy these sticky tabs? So you buy a set of sticky tabs, and you can put those on your circuit breakers, right? They're little tiny sticky tabs. And then after you've done that, let's say this maybe costs hundreds of dollars, and that wouldn't be a bad projection for based on our cost estimates. And you can basically glue these things on your circuit breakers, and then by doing that, you can essentially sub-meter your home by looking at the currents that are flowing through the circuit breakers. So that's one idea, and you can maybe glue those things as well on your power cords, and then achieve sub-metering in that way. So here again some of the applications. The two that we're working towards right now is again sort of the smart grid application, where we look at these low-cost sensors for underground cables. That would be ideal as well. Specifically in the underground cable case, we're not able to. We don't have access to other energy like solar power, for example. So in that case, we really need to scavenge the energy from the conductors itself. And then if we reduce the size of that sensor a bit, we can maybe embed these things into the power cords, like I mentioned. And then finally, we can maybe achieve the sticky tabs, where things can essentially be glued on. These sensors can be glued on, and we can actually connect wirelessly to these things to measure the power in the circuits. So in fact, we're kind of doing that already, except using bigger components. And Richard Su is actually leading that effort. And so what we're doing here is using actually a set of mesoscale current sensors, which can also be used as scavengers, and put them onto circuit breakers, and then see if we can sub-meter several panels in Corey Hall using that idea. And so in fact, that work is in progress, and hopefully soon we can report some exciting results from that project. All right, so let me talk now about the two sort of main components of this module, specifically the proximity sensing. So one of the advantages with the proximity sensing is that it is completely non-invasive. There is no galvanic contact. We simply put the sensor in the vicinity of the circuit it's supposed to measure. And so that allows us then to encapsulate the entire module. and make it hermetic so that it doesn't degrade over time. There is no moisture penetration into the system. Using MEMS, we make these things be really inexpensive and small. And then, of course, since they're MEMS, we can make them use not much power. So as I mentioned, the current sensor has actually been developed before by Chris Sherman and Eli Leland, and Chris is actually perfecting this right now. Voltage and power sensors is what we're working on right now. And we have some conceptual designs. We're actually starting fabrication of these things shortly. Going back to the current sensor, these are just some of the results. It is essentially using a MEMS cantilever beam that is coated with piezoelectric material. And then a permanent magnet is deposited using a printed magnetic method that was developed in-house. So it's actually developed, it's printed on top of this cantilever beam. And then when that beam is placed nearby a current-carrying conductor, or for example a zip cord, you can actually see motion up and down. And that motion is then transduced through the piezoelectric material to a voltage that can be measured. And so there is very good linearity here. These sensors are designed to have a very high bandwidth, and so there is no excitations of any modes, any significant modes at the power frequency. So you can see a very, very linear response of the sensor. Of course, the signal of the sensor is a little bit weak, so it still requires amplification. However, altogether, it allows for a very low power solution. This is the work that we're continuing on the electric field sensing. We're essentially using the capacitive methods to sense the electric field from the conductors. The interesting thing about MEMS in this application is that because we can make these sensors really small, we can really take a point field measurements. And so by looking at the gradient, so differences between several of these points where we measure the field, and if we know some of the geometry of the wire, we can actually we can calibrate the sensor automatically because we know the gradient, right? So we can figure out what the field should be. And this just sort of shows the field between two neighboring conductors. The other interesting thing here is that because of the nature of these conductors, or essentially the field is emanating away from conductors, there's actually very high potential that is being capacitively coupled really quickly. So it allows us to get actually a pretty clear signal out of these sensors. But again, at this point, we have a few designs that we're modeling and investigating, and we're starting fabrication of these things shortly. Diagnostic sensors. As I mentioned, I believe diagnostic sensors will be an important part of the smart grid, just because the grid is going to be stressed more, and so we really would need these sensors to tell us, when an equipment is being degraded to a point where we can't really send all the power that we think through it, like an underground power distribution cable. So this is some of the sensors that we are investigating specifically for those things. We're looking at, if this actually shows your underground power distribution cable. I should actually mention the components here. This is a central conductor, and there is a little semicon layer that smooths out the field a little bit. There is an insulating layer, so that's the insulator. And then there is another layer of semicon, again, to smooth out the field. And then there is a shield of concentric neutral wires around this, surrounding the insulator. And that provides both the path for return fault current as well as a path for imbalance current. And then there's a jacket in the modern cables. And so what we try to do, and so we actually developed some methods in a related project funded by the California Energy Commission to measure or to probe the integrity of these cables without disconnecting the cable out of service. And so we have some very promising techniques that allows us to detect both the integrity of the concentric neutrals as well as detect the integrity of the insulator. And so again, the idea there is that we can have this sensor that, yes, measures the flow of power through the system, but also can tell you when the cable is going to fail, or more importantly, can tell you how soon does it project the failure. So if we can measure degradation in the insulator, if the sensor can say, oh, well, look, it looks like, I have maybe 2 years of lifetime left, that would allow the utilities then to come in and schedule time where the system can be taken offline, power can be rerouted otherwise, right? And to change this cable out without, disruptive event like a power loss. And of course, once these cables go, there is actually a brief connection between the neutral wires and the central conductor. And so the cable actually explodes, and that also poses a hazard. There are people who are being killed, or I wouldn't say killed, but damaged by flying manholes. So, okay. So that was sort of briefly about our work on proximity sensing. Let's move on to energy scavenging. And so the idea there is to extract power from the conducting wire. And so our approach is actually to use a transduction from an electrical to mechanical and then back to electrical domain. And so it's essentially the same technology we use for current sensing, except this time we optimize it for scavenging. So if this is your current carrying conductor, it will be surrounded by a magnetic field in the presence of an AC current. And so what we do is we place a magnet in that magnetic field, in the proximity of the conductor. The force on this magnet then will, is according to that equation. We have some magnetization vector. And so what happens is this magnet actually moves up and down. The beam then resonates. We have a piezoelectric layer then that we couple to extract power from it. And so, that's initially to the magnet we couple from the electrical to mechanical. And we have this beam resonating and electrical. So the interesting thing with this system is that, first of all, the strength of the magnet provides a very strong coupling to the wire itself. So, the inverse problem really is looking at, how much force on the wire in presence of a strong magnetic field, right? Sum of forces equals to 0. So it's sort of a dual problem. And so it turns out that we actually have a very good coupling. We can use a very strong magnets to do the coupling. And then we can design this thing to work at resonance. So we're actually pumping up sort of a mechanical system that resonates. We're storing the energy mechanically in a resonating system. And that allows a very good coupling on this end. And then we're working on improving the piezoelectrical coupling on this end. So that's the basis of the technology. The interesting thing there is that it actually works very well. So we're currently still in the process of doing the comparison of merit, but at this point it looks like we're clearly not doing as well with the current transformer. So if you can surround the wire with a magnetic system, a current loop, this is really the way to go. However, for our applications where you have a stick-on sensor, we don't want to be surrounding the wire. And so now the coupling with the magnets really seems to provide a fair amount of power. So we're looking at about at least an order of magnitude of power above the other approaches just using a coil. Okay, this shows sort of again a schematic view of our energy scavenging system. There are, of course, some implications here. We need the transducer is really one part of it. We need some power conditioning, where we convert the power from AC to DC. Some storage, where we store the power for use by our system and when we're going to take the measurements. And then a very important part in this mechanical system is overcurrent protection. This is actually not a problem with the coils, right? So if there's either a lightning strike or current exceeds the amount of the mechanical system, we need to be able to prevent this beam from exceeding the yield strength of the material and essentially causing damage to itself. And so, so this is one very important thing of our system to actually have reliable operation, long-term operation. As I mentioned before, we're looking at two approaches. We're looking at the Mesoscale approach, which essentially using PZT bimorph cantilever beam. We buy off-the-shelf strong neodymium magnets. And actually, Richard Su figured out a very interesting circuit. So by using two magnets with reverse polarity, we can optimally couple to a current-carrying conductor. Now, the goal of really of this mesoscale approach is to provide as much power as we can to the system. For the MEMS approach, the goal here is now to not so much the power, but to reduce the size of the system. So what we want to have is kind of like a microchip that you can put on a PCB board, and that doesn't really look any different than any other microchip on that board, but still provides power. And so what we've done there is we've essentially used, taking that cantilever beam and so bend it around, sort of like a meandering spring inside the system to provide a MEMS spring, a MEMS device that, with this given proof mass, still resonates at 60 hertz. So that's why it looks a little bit strange here, but that's really just taking that cantilever, making sure we still keep a 60 hertz or a power frequency, or 50 hertz in the Europe resonating frequency, and we can put it into a MEMS package. And this sort of shows also that that system is designed to actually work with a zip cord. On a zip cord, the problem is that you have power, returning power next to the power that comes out. So it's sort of a loop where two conductors are put next to each other. And if you use a current transformer on that, the magnetic field actually cancels. So you cannot get a decent measurement. So our system actually is able to harvest power from that. This is just some of the results. I'm just going to actually quickly go over it. From the mesoscale, so the big beam harvester, we can actually get, we've demonstrated that with our current system, which is not really optimized all that much, we get 11 milliwatts from 50 amps RMS. And so 11 milliwatts is actually enough to transmit continuously, 100% duty cycle, using some of these low power radios that we have. And then, of course, we're looking at some overcurrent protection. And Richard Su did some very interesting simulations lately with match very well with the actual experimental results. So it seems like we have a very good way of getting the power out of the system, so the mechanical power in overcurrent conditions. So that's good because that's really an essential part of our system. For the MEMS, a MEMS device, again, this is not really designed to produce a lot of power, but again, to just fit within that small package. It is, we're working on actually fabricating this right now. And in fact, Doison, visiting from Norway, helped us with the fabrication of that quite a lot. And you can actually see the electrodes have to be patterned in a very specific way in that device because we have both tensile and compressive stress. So on the piezoelectric layer, we get both, different opposing polarities of charges being generated. The power is not too impressive. Our modeling suggests we're going to get on the order of 2 microwatts from the current system. This is just with a single piezoelectric layer. We can improve it to 10 microwatts with a little bit different design. But even this is enough to trickle charge a capacitor and then use that power, at a low duty cycle to take measurements. Right, so we're actually kind of excited about that, even if it's not that much. This is just the fabrication process. I'm going to quickly skip over that. And that was actually everything I had on the harvester. So looks like this is about the right time to do this. So conclusion. Really, sort of the point I would like to make here is that I think smart grid really, and in smart grid in whatever form it comes or it should come, but in essence, power system sensing really presents an opportunity for MEMS because of just the amazing size of the system and the size of the problem. And we can use the toolbox that we know in MEMS to really reduce the cost of these sensors to a point where they can really be massively distributed throughout the grid and also throughout the residential and commercial settings. So we have some toolbox there. We are currently developing sort of version 2.0 of this stick-on sensor module, and even with this sensor module and with the price we're looking at for, let's say, mass fabrication, this is really a very attractive device that can be used hopefully to instrument at least parts of the grid. And we're talking with some of the utilities about this at this very moment. And then ultimately, the goal will be to have something like a little stick-ons that you can buy in the Home Depot for not very much money to be able to instrument your home. And of course, if these things are so small, maybe we can all buy the extension cords and all the appliances that already have these systems embedded in them. We can simply pull up a Bluetooth connection on our laptop and then see whatever power we're using in our homes. Now, the other interesting thing I would like to mention here is that there are actually, some of these problems may seem simple, but it's really some fascinating problems that come up, from an academic sense. So, for example, overcurrent protection. It's a tricky problem. How do you design a system that efficiently, collects energy and stores energy in a resonating mechanical circuit, but then when needed, quickly dissipates it, right? How do you do that? How can we all of a sudden reduce the Q to almost nothing, from a very high Q system? Energy scavenging. How small can we really make these energy scavengers? We're looking at a system that's 1 by 1 centimeter. Can we make it 1 by 1 millimeter, right? Can we make it so small that it can really be integrated, into, again, a power cord? If it's 1 by 1 millimeter, it's essentially a small system that could be put in there seamlessly. What are the theoretical limits? How do we do power conditioning efficiently? Benign sensor placement. Whenever we talk about new technology to our partners in the utilities, they get a little bit nervous. And so they get nervous in the sense that the systems they have now, they work, and they work fairly well. But even though they work well, we would like to put some sensors in there. How can we convince them that placing that sensor into that jacket doesn't degrade the functionality of their system, of the cable, right? So that's one thing we're looking at. That's very interesting to be able to prove that, to do some longevity testing. And then, talking about longevity, how can we create systems or sensors that after 40 years plus of service will then all of a sudden wake up and say, oh, this cable needs replacement, right? Again, how do we test? How do we even test something that's supposed to be working, for 40 years? So sort of the big view of this is, I think, lots of exciting problems. And I really think that, that MEMS can provide some really exciting solutions to solve these problems for the time to come. So that actually concludes my talk.
Thanks, Igor. So let's open the floor for questions. I got one right here.
Yeah, Igor, so your slide about trickle charging a capacitor, how much energy do you need to harvest from that capacitor in order to communicate the useful information to whatever would be collecting and processing that information? And, right. Or how often can that capacitor or can that circuit communicate, per day if it's harvesting 2 microwatts or 11 microwatts?
Right. I mean, so it depends. It depends a lot on the rest of your system, of course, right? How low your power radio is, what kind of duty cycle you can have, what kind of losses you have along the way, right? As you do rectification, just things like, what is the voltage coming out of your harvester? If it's a low power but high voltage harvester, you can avoid problems like losses in the diodes that maybe rectify the system. But I think sort of the useful number that we've been using was 2 microwatts. And so 2 microwatts has actually been shown by some other researchers in our group to be able to provide, modeled, right, with all the losses, to be able to provide enough power to achieve a reasonable duty cycle of communication and still trickle charge a capacitor. For measurement.
So what is that duty cycle for 2 microwatts?
Yeah, I actually don't remember the number off the top of my head, but it's more than once a day, right?
More questions?
I'll just yell.
Well, this is broadcast on the internet, so we need the microphone.
Very interesting. At scale, do you have any estimates on version 2 costs?
The scale, yes. At the scale, we're looking at tens of dollars, so $10. Roughly.
$10, okay. And the radio signal that you're talking about, how far would that be able to broadcast? So, in terms of proximity to some sensing.
Okay. So we've measured some of the modes we're looking at. The range is about 100 feet, right? So you can imagine having a wireless low-power mesh network that is then, uses some repeater nodes, right, if we need to, that essentially, transmits that signal, let's say, along the power line to a base station that then has, more transmission capabilities. So that's the model we're actually shooting for.
More questions? Okay.
In your sensor section, you showed it looked like a separate device for the power sensing.
Right.
Can you describe that?
Okay, so for the sensor, it's essentially using the same technology for sensing as scavenging, right? But for the sensor, you would like the device to be off resonance, and in fact have as high eigenfrequency as possible, because you would like to have high bandwidth. You would like to be able to track that cycle, right, the power cycle. Now, for the harvester, you really would like to use that mechanical resonance as a storage from which then you can extract more energy, essentially. So the short answer is the sensor has to be off resonance, the harvester has to be at resonance, and hence it requires two different devices.
What's limiting the power on the harvester? If you make it bigger, can you get more than 2 microwatts?
That's a good question. Well, so yes, of course you can. You can add, obviously, several of these harvesters together and then get more power. So it actually, just because of sort of the overhead of the material and the way you have to, there's always some losses in how you pattern these things. So in general, the higher you get, the bigger your harvester is, the more power you get out per sort of square inch. The power density increases. But of course, there is the form factor limiting factor as well. And then in this case, now that I think of it, it's actually also the fact that our magnet, if you move further away from the conductor, you're going to lose some power. So I think actually that ratio flattens out. So I believe it's simply you would just add more of these things in parallel and you would get the same ratio. So if you have space, I don't think there is much limit.
Okay. More questions? That's it. Well, thanks, Igor.
Great, thank you.